Audio Jungle. Audio Jungle.
So Rankine half body, okay, Rankine half body, or also you can call it flow past a half body. Also it can be it can be it's a combination of source and uniform flow, okay, source plus uniform. So this is also one kind of objective question, no? What is the objective question? You can think here, you can, like, they can ask what is the uh, s- what superimposed flow called if if flows are source and uniform flow, okay, or they can ask also it's a kind of MCQ, like Rankine half body flow. Options will be source and sink pair flow, tablet flow, source plus uniform flow, none of the above. Other also question also can make flow past half body flow will be source and sink pair, source plus uniform flow, okay, only uniform flow, none of the above. So for that reason all three name I have given, but meaning will be same, okay, all three name I have given but meaning will be same. All right, now so the question, now hope you understood how they can ask. That is one thing. I mean, based on the combination of the flow, they can ask question. Okay, the combination of source and uniform flow called as Rankine full body flow, Rankine half body flow past half body, flow past full body, something like that. Okay, that is one thing. Second thing, now suppose flow source and uniform it is given, then pattern we have to draw. We have to check the pattern. What will be the pattern? And based on the pattern we also have to calculate the parameters. What are the parameters? Parameters are like what is the tangential velocity, if there is radial velocity, so what will be the radial velocity, what is the stagnation point, okay, all those things that question also can ask. Okay, it's not all about only GATE Aerospace. We are also talking parallelly about GATE XC. So for XC GATE, these are very pet question. From this topic, these question they are asking every time. It's not only one question, 4 5 questions. Okay, so just listen carefully, and it's very simple concept. So wherever derivation is required, I will give. Where it is not required, direct result I will provide to you, so that in that way we can save our time. Right. Now so we have the combination of source and uniform flow, and we'll see the pattern. So I can say source flow I'm taking here parallel to x-axis, okay, anything you can take, but here I'm taking source uniform flow which is parallel to x-axis. We have uniform flow parallel to x-axis, and next, that combination, what is the combination is uniform plus source flow. So this is what source flow there, this is what source flow, check, this is nothing but source flow. Flow is coming out from a point called source flow, so this is the source flow now. Okay, this is what source flow, right, this is the source flow. So I can write here, it's a uniform flow, and this is what source flow. What will be the pattern? Now you just listen carefully, very soon you will understand everything. So for source flow, obviously this is the source flow here, this is the source flow, and once it is source flow, so definitely flow will be coming outside. That is one thing, and that is true also. So the both flow you have to map at map for the single diagram, because this two different diagram we have, that is uniform and source. Okay, uniform and source. Now we have to map, superimpose this uniform and source flow, then how it looks like, that is the point, and we need to draw based on that. So we can say this is what source flow. So source flow, obviously this flow will come in this way, and at the same time uniform flow also coming towards the source flow. You can check this point and this point, so both are just opposite each other, right? So I can say, because both these are the streamlines, obviously these are the streamlines, so this streamline and this streamline both are just opposite. Both are just opposite, so it will meet somewhere. So I can show you that it is meeting at this point, it is meeting at this point. Okay, now, so later on I will give the naming of this point also, but I can say, because uniform is what continuously it is coming like this, it is coming like this. See, this is the uniform flow, this is what the uniform flow, this is what the uniform flow, right? At the same time this source flow also coming. Source flow means the flow is what coming out from the points, so obviously it will come. So once it will comes in this direction, so but this source flow will try to push this this uniform flow, or this uniform stream line will try to push this streamline, because obviously streamline cannot intersect to each other, that is true, but it can push, it can push this uniform flow, can push this source flow. So how this flow will be? It will go in this way, but once uniform flow will push, it will go like this. Similarly, this source flow will also try in this direction. It will also try in this direction, but this uniform flow will push and it will go like this. Okay. Similarly, other also, all the streams lines make a path like this. I mean, will the pattern will be like this. See, like this. Here also streamlines, and these are streamlines, since they are not going to intersect to each other, that already I have told you. Parallelly it will go, but it will never intersect to each other, and why it cannot intersect, that also I have given the reason, also I had explained that. These are the streamlines. Now, so this basically, this uniform flow, obviously it will be like this, it will be like this, right? This uniform flow will be like this. Here also it is like this. So once uniform flow and source flow will superimpose, then this type of flow pattern will come into picture, right? I hope this one is very clear. Obviously, because this is the source flow, so source flow will also go in this way, because this is the source of flow is what coming outside from the source. This is the source, this is the source. There should not be any confusion. As you have seen, these red lines are the uniform flow. So uniform flow and source flow, because source is what coming outside, so a uniform flow, and see this source streamlines and this uniform streamlines, somewhere they will it will create one lines. Obviously it will not cross to each other, but if you check the pattern, the flow is what coming outside, and this flow uniform flow is what coming towards the source flow. So somewhere it will meet to each other. That boundary I have to show you, and that is the imaginary boundary. That imaginary boundary will be just like a, it's a, it's a representation that uniform flow and source flow that cannot cross to each other, and that is nothing but this red line. So it is a imaginary boundary. This imaginary boundary will be separating uniform flow as well as source flow, because that you know very well, like streamline cannot cross to each other. So this uniform flow will also have a streamline, source flow will also have a streamline. So they will push to each other. Source flow will coming outside and uniform flow coming towards the uniform flow coming towards the source flow. So they will push to each other, obviously, but they will not cross to each other. So once they are pushing to each other, so obviously one imaginary boundary will be created. That is nothing but this red line. This red line is the boundary, and it's a interpretation that it's showing a kind of imaginary boundary, means inside that only source flow will exist and outside only uniform flow will exist. They are pushing to each other. For that reason, now this new pattern you got, but they are not crossing to each other because both are streamlined and they cannot intersect. So this red lines, it's just like a boundary. Okay. And if you check this body red lines, it's a, I told you it's a boundary, so it's also called a body, imaginary body. That means it's a one, it's a just like or similar to a physical obstacle, you can say. Physical obstacle is there, and the flow cannot that flow cannot enter, or it cannot cross this boundary. That's the mean of it. Okay. So and if you check this boundary, which is also called an imaginary body, and if you check this imaginary body, it is open. It is open here at this end, and top and bottom red lines, if you check, it is open. It is not going to close somewhere, because if it will close, so when it will be closed, when there is another sink is there, so all the flow streamline will be synced towards the sink point, but we do not have any other sink, only source is available, hence the flow continuously, all the streamlines will be open to infinite. It is not going to close somewhere. So you can check this body, which is nothing but imaginary body, red one, this imaginary body, imaginary wall, you can say imaginary body. And if you see this imaginary body, this is open, so that's the reason it is called half body. Half body is not a full body. Full body means the complete structure, but it's open, hence it is called half body. For that reason, it is this combination source and uniform flow combination, also called as a Rankine half body, also called as a flow past a half body. See, we have a half body here, red lines, you can check dotted, these red lines, it's a half body, and flow past the half body we have. These are the uniform flow. Who has accomplished this half body concept? Rankine, that scientist name, hence it is called Rankine half body. A simple idea only, right? So our analysis up to this, it is very clear. You got that. Okay, these red lines are the imaginary wall where the streamline cannot intersect. So if it is not intersecting, it means there is no across flow. If there is no across flow, we can consider it's a imaginary wall or body. Now, if you check exactly at this point here, where I'm marking this, so this point is very special for you. Why? Because if you check at this point I'm talking, this is the source flow. So flow is coming in this way, and this is the uniform flow, and flow is what coming in this way. See, uniform flow and source flow just opposite, and opposite streamlines once comes and hit, so somewhere it will make zero velocity. For that reason, this point will be the stagnation point. What is the mean of stagnation point? Yeah, right. So stagnation point, right? This will be the stagnation point. If you see, uniform flow will have some velocity. Source flow will also have some radial velocity. There is no tangential velocity. Source flow, as I have explained already in previous lectures. So we'll have a radial velocity, and uniform also along the x direction will have a velocity. Once both streamlines comes with some velocity, and it's just opposite to each other. So for instant of time, that velocity reduced to zero. Simple. Velocity is the vector quantity, so obviously we'll see that just opposite, and if it comes and hit to each other, obviously you can say it reduced to zero for an instant of time. So it velocity reduced to zero, it means it's a stagnation point. Stagnation point means where the velocity is zero, that is called a stagnation point. Simple idea only, that basic you have to use. Now our all analysis, if you see this for Rankine half body, if you check this stagnation point and this is what source, this value they are asking in examination. This is the source now and this is what the stagnation point. Source and stagnation point. So from the source, what is the location of stagnation point? It's nothing but R S, radial distance of S for stagnation, R for radial distance. Radial distance for stagnation points, which is very important. They are asking in examination, right? Anyway, now, so one by one, we'll see all the calculations. So I'm just going to take this Rankine half body and we have to work on it. So everything will be clear. Okay. Now, coming to the next, I can show you this Rankine half body here separately. Now I can remove this. So uniform and source flow, only Rankine half body I will show you. So I can take red lines only. So it will be more clear. Red lines. So okay, I can check in between. I can take right now. Right, right. Now see this, we have a hash line. This hash line will show you that imaginary body. Okay, it's an imaginary body and the flow is inside. Flow will not go outside, outside flow will not go inside. Okay, obviously just now here you have seen we have source somewhere here. See, we have a source somewhere. This is the source and this is the stagnation point. Distance between stagnation point and source is nothing but RS. This is stagnation point. Stagnation point. Okay. Now, rest this side we have a uniform flow plus source flow. Now, uniform flow plus source flow. Then you will get this Rankine half body. Now, each and everything we have to calculate first. Calculate for this Rankine half body. What we have to write? First, we'll write the stream function and then we'll write the potential function also at the same time, right? So if you write the equation of stream function, equation of stream function, then what is the psi? Psi is the equation of stream function. What is the psi? Psi is nothing but psi is equal to uniform flow. This is uniform flow. Uniform flow. Uniform flow. And this is what? Uniform plus stream function of source flow. You know very well, for parallel to x-axis, this flow, if you uniform flow, if you check, it was parallel to x-axis and parallel to x-axis, this one. I can say parallel to x-axis and the velocity is nothing but v. So parallel to x-axis, it means small u is equal to capital V and small v is equal to 0. That already I have explained how. Okay. So For that, if you remember, I had calculated psi uniform flow for parallel to x-axis. So it was Vy. If I'm correct, then this was the psi for uniform flow. We had calculated that. Plus psi of source flow. If you remember, psi of source flow we also have calculated. It was q by 2 pi into theta. Agree with me? This was the formula we had calculated. For source flow, already this formula I had given, q by 2 pi theta, and uniform flow psi, that is a stream function, it was v into y, right? Now if you check there, here second term we have a 2 q by 2 pi theta. Theta is that an angle basically, and in first it is y is nothing but Cartesian. So r and theta for the polar and y is Cartesian, so it is not matched. So one thing we can do, we can convert both in polar form, or we can convert both in Cartesian form. So always remember, converting Cartesian into polar is very easy. So what is the concept to write Cartesian simple into polar, or polar into Cartesian? See, this is what r, radial distance. This angle is what theta. Okay, this is x, and this is what y. So this Cartesian, if you convert into theta, what you will have? What is the y? Y is nothing but this side component will be r sine theta. So y is nothing but r sine. Okay, x is nothing but r cos theta. So we are interested about y. So we can keep y is equal to r sine theta. So both component will be in polar format. Okay. So now what is the stream function psi? Psi is nothing but just now psi uniform flow plus psi source flow. Here you got psi uniform in polar format. Y is nothing but just now you have written r sine theta. So this will be v r sine theta plus q by 2 pi theta. Now we have to increase our speed little bit, because now the basic concept now you got here. Now we simply will have to perform some calculation. So this is the stream function, okay, equation. Anyone you have to take, it's your choice, but sometimes potential function also required. So equation of potential function. So what is the equation of potential function? You can write psi for the phi is equal to phi of uniform flow plus phi of source flow. Phi of uniform flow, if you remember, it was Vx, and phi of source flow, if you remember, it was q by 2 pi ln r. This all I have derived, okay. V into x, just now I have converted into polar form, r cos theta plus q by 2 pi ln r. This is nothing but phi. That is the potential function for the Rankine half body. Okay, I can write here equation of potential function for Rankine half body, and this is what we have calculated, equation of stream function for Rankine half body, right? Okay, now coming to the, which is very important point, that is the stagnation point, okay, or we can go for the velocity components. So this is the new heading, calculation of velocity component. Okay, so we have to calculate all the velocity components, like how many velocity will have, obviously radial velocity and tangential velocity. What is the radial velocity? See, what is the radial velocity? Number one, If you see the formula 1 by r dou psi by dou theta, this is the formula. Already I have given to you. So 1 by r dou by dou theta of psi. What is the psi? Just now you have written here. See this psi value. It is Vr sin theta plus q upon 2 pi theta. It's a Vr sin theta plus q upon 2 pi theta. You have to differentiate. So you can take r inside, so r will be cancelled out. Even you can take outside also if you differentiate with respect to theta. So what you will have, a v r sin theta becomes cos theta differentiation q upon 2 pi. Theta differentiation will be 1. So this is the value. Now you can take r inside, so it's nothing but v cos theta plus q upon 2 pi r. Remember, this is the radial velocity you have calculated. Radial velocity you have calculated for velocity component for what? For Rankine half body, RHB. Okay, Rankine half body. This is very important. What it is going on, you just focus on it. It's very, very important for your exam. Okay, Rankine half body, this is the radial velocity. Now coming to the tangential velocity then. What is the tangential velocity? So theta. What is the v theta? So you have to use the formula. Any formula you can use, stream function or potential function. It's your choice. V theta, you know, dou psi by dou r, right? Minus 1 by dou r in bracket psi. What was the psi? If you remember, Vr sin theta plus q upon 2 pi into theta. This is the value of psi. Now you differentiate with minus sign, keep outside, so it becomes a v sin theta plus this will be 0. Simple. Second component do not have any r function, so it becomes 0. What is the tangential velocity? V theta. V theta is the tangential velocity, and it's nothing but minus of c minus of v sin theta. Very, very important. Directly they can ask question, what is the tangential velocity in case of Rankine half body? Or they can ask like, okay, when the combined flow of uniform and source flow, then what will be the resultant tangential velocity for the combined flow? So resultant velocity, resultant or tangential velocity for the combined flow. Now what will be the combined flow? Obviously Rankine half body, because combination of uniform and source they have given, it means it's a Rankine half body. So indirectly they are asking what is the tangential velocity for Rankine half body. So if you remember minus v sin theta, you can directly answer for it. Okay. Now, so you have Vr, that is radial velocity, and you have v theta, that is nothing but tangential velocity. Now if they ask what is the resultant velocity, that also you can calculate. What is the resultant velocity? See, so resultant velocity means v capital R. Okay, resultant velocity means v capital R. So it's nothing but v radial square plus v tangential square into root. You have to calculate, and whatever the value you will get, you can keep inside, though you will get the answer. Okay, the story is not end up here. What is very important point they are asking? They are asking tangential velocity, radial velocity, you have calculated. They are asking also resultant velocity, that also you have calculated. Okay. Now coming to the stagnation point, we have to calculate stagnation point. That is very, very important. Okay. Now how you will calculate stagnation point? It's very simple. If I say stagnation point, so by definition, you know, stagnation point means where all the velocity is what? 0. Stagnation point, if I say all the velocity, means anything, tangential velocity, radial velocity, anything, total resultant velocity will be 0. Okay, you can write separately also. Vr will be 0, v radial velocity will be 0, v tangential velocity, means the total velocity will be 0. That's the mean of it. Okay, so to get the stagnation point, radial, obviously radial distance you are interested to calculate, or maybe tangential value also, but Here, if you see the diagram, r and theta, polar format. Why? Because see, I can show you this diagram again, so you will understand clearly. If you are interested to get r value, this is rs. So I can ensure this diagram, what you have drawn, it's perfect. But again, I would suggest you can take any points here. This point is nothing but p. Okay, this point is nothing but p. You can say this point is p x comma y, or also you can say r comma theta. You can take, because this is the source, so from here toward this distance you can take r, and this angle you can take theta. So if this r will reach from, suppose this is p and now this is o, if this point p and this is what source s, okay, if this r p point suppose shifted to o, then this r will be r is equal to rs. Okay, at this point, what is the r is equal to rs, because you have given here, see this distance, right? So hope this one is clear. And at r is equal to rs will be your stagnation point. What will be the theta? So theta is what increasing in this way. So at point o, what is the theta? Theta is 180 degree, simple, just opposite now, because you are measuring from here. If you measuring angle, so from here to here, what is the angle made? It's a 180 degree. Okay, from here to here, huh? So because this is the one straight line, so from this angle to you are measuring here, so here means that this point, so obviously this angle will be 180 degree, simple. So there should not be any doubt. So what is the polar format, polar form? That is r theta. And in terms of polar form, if you are interested to calculate stagnation point, so it's very clear. At stagnation point, theta will be 180 degree. There is no doubt about it. R value we do not know. We have to calculate. So how we'll calculate? We'll make all velocity component zero at stagnation point. Okay, that you know very well. So any velocity we can take, Vr we can take, or V theta. But if you see V theta, you make zero. If you make V theta zero, then what you will get? Check, I'll show you. One by one, I'll show you. If you make V theta is equal to zero for a stagnation point, because at stagnation point, V theta should be zero. And what is the V theta? That is V minus V sine theta, right? And this should be zero. If this should be zero, so obviously V will be zero. Okay, so that time sine theta, automatically that value will be zero. This V and this sine theta, so this capital V will not be zero. Why? Because this capital V becomes zero, it means there is no uniform flow, but uniform flow is there. To have uniform flow, this capital V should not be zero. So this sine theta must be zero. If sine theta becomes zero, then what is the theta? You can see theta is nothing but pi. Maybe zero, maybe pi. So zero is not possible, because from where you are measuring at this point. You are measuring theta from this point. If you are measuring theta from this point, so if theta becomes zero, then what is the point? Nothing. But theta becomes 180 means you are reached at this point, just opposite to this. That will be 180 degree. So it is very clear, stagnation point, theta value will be 180 degree. At stagnation point, this can be asked for 1 marks. For Rankine half body, at stagnation point, theta will be 0, theta will be 90, theta will be 180, theta will be 270. What is correct answer? Theta will be 180. Just now you have proved. And anything, if you are proving, that is one thing, but physically by the diagram also you have to imagine, so that will be more clear in your mind and you can remember in that way. Okay, anyway, so it's very clear, theta becomes pi. Now to make Vr is equal to 0, because we are interested about the stagnation point. So if Vr, you check, Vr is nothing but, what was the value? If I'm not wrong, it was the Vr, wait, V sin theta, V cos theta plus Q upon 2 pi r. V cos theta plus Q upon 2 pi r. Now check. What should be the Vr, radial velocity at stagnation point? It should be 0. At stagnation point, what is the theta? Theta is pi. Just now you have calculated here. See, this theta is nothing but pi at stagnation point. So this theta becomes pi plus Q upon 2 pi r. What is the r at stagnation point? What is the r at stagnation point? Just now I have shown you. R will be RS. Again, you go to the diagram and you just clear. See, at stagnation point, what is the R? R is nothing but RS. Okay, so theta will be 180 at stagnation point and R is equal to RS. That RS value we need. Okay, so R is equal to RS. We can write here RS. Now check. So it's a 0 already. V cos pi. Cos pi is nothing but cos 180. Cos 180 is nothing but minus, I think, right? Cos 180 is nothing but, I think, minus value. Minus 1. Cos 180. Yes or no? What is the cos 180? Cos pi value? Anybody? What is cos pi? It's a minus 1. It's a minus 1. Okay. Plus q upon 2 pi rs. Now if you calculate rs, it's a v will go this side, so it's nothing but v. Okay, and rs will be q. So obviously q v will come in denominator, so it's nothing but q upon 2 pi v. This is very special value. So very, very important. Okay, this is nothing but stagnation point, radial direction. If I say what is the stagnation point basically, so only one stagnation point you will get, okay, in Rankine half body, only one stagnation point. And if you see stagnation point here, r theta, what is the stagnation point? R is nothing but rs, that is nothing but q upon 2 pi v, okay, 2 pi v, and theta is nothing but 180 degree, or you can say pi. This is very, very important. Okay, this is very, very important for your examination. This is the one thing. Again, the question they can ask, like, okay, if you see the rs stagnation point, that rs is what? This relation you can check. Basically, this rs is equal to what? You got q upon 2 pi v. So rs is directly proportional to q. What is the q strength of? Source. Rs is also inversely proportional to velocity. What is the v? Uniform velocity. Uniform velocity. Intensity of uniform velocity, or simple uniform velocity. So this result you remember. They can ask, if uniform velocity v is increasing, then what will be stagnation point? It will be reducing. Okay, if q strength of source is what? Q is increasing, then what will be the stagnation point? Stagnation point also will be increasing, and that result you need to remember. Your job. That is one thing. The last one, which is very important, what they can ask equation of streamline passing through the stagnation point. I am interested about the equation of streamline passing through the stagnation point. Here we can write equation of streamline passing through stagnation point, or इसी को और क्या लिख सकते हो? We can write or equation of streamline, equation of streamline for Rankine half body. Okay, और इसी को और क्या लिख सकते हो? और equation of streamline for imaginary wall. कौन सा imaginary wall? See, we can give the name also for that wall. What is the wall here? See, for this wall we are interested to write the equation. See here, just give me time. This wall, I can give the name. This is A and this is B. So for AB wall, because this AB wall is what passing through the stagnation point, so we can give the like heading equation of streamline passing through the stagnation point, that is also correct. Equation of streamline for the Rankine half body, that is also correct. Equation of streamline for imaginary wall, because this imaginary wall itself is passing through the stagnation point, so meaning will be same. So now we are interested about this imaginary wall, and we are writing equation of imaginary wall, okay, which is passing through the stagnation point, right? So what will be the value? That is very interesting and very important. Now see, just now you have seen the equation of streamline. Simply just now you have seen equation of streamline. Huh? What is the equation of streamline you have seen? It was psi, and psi is equal to, just now you had seen, psi is equal to uniform flow plus psi is equal to source flow, and just now you have written the value in starting only. In starting only you had written value. What was that? See, what was that? It was psi of uniform. You had written VR sin theta plus psi of source flow. You had written q upon 2 pi. Just turn your pages, you will get it, okay? This value. Now if you are going to write psi of this Rankine half body, okay, psi of this Rankine half body, which is passing through the stagnation point. So what you will do? What you will do, which is passing through the stagnation point. So all value you have to satisfy it, because it is passing through stagnation point. Then R will be Rs sine theta. Theta will be pi. Yes or no? Plus q upon 2 pi. Theta will be pi, because it is passing through the stagnation point. So that stagnation point should satisfy. Now V Rs, just now you have proved. What was the Rs? If you remember, it was q upon 2 pi V. Okay. Sine pi. What is the sine pi? Sine 180. And you know, sine 180, if you remember, it's nothing but 0. So I should put here 0. Huh?
Sir, minus.
Sine pi is minus 1. No, sine pi is that is 180. Sine 180 is 0. Huh? Sine 180 is 0, right? It's a 0 value plus q upon 2 pi. Pi cancel out. You will have a q by 2. So psi of means equation of streamline for Rankine half body for imaginary valve, you can say it's nothing but q by 2. This is very special here. Very special. Okay. Always remember this value. Anytime in exam they can ask to you. Right. This is very important, and we were interested about it. So if you see the streamline passing through the stagnation point, okay, and basically it's like a virtual solid surface, okay, this is streamline, because if you see the value, it's q by t, that is the strength of source, half of the strength of source. What is q? Q is nothing but strength of source. So psi of Rankine half body, physically what is the mean? It's a half of, this is also very important, half of strength of source. They can ask question, what is the equation of Rankine half body? Option will be strength equal to strength of source, 2 times of strength of source, half of the strength of source, none of the above. So if you know that, then you can write half of the strength of source. What is q? It's a strength of source. So Rankine half body equation means whatever the imaginary wall just now you have seen, it's a, I had shown you the separate color, it was red colors. That is the imaginary wall basically, and that indicating that inside flow will not go outside and outside flow will not enter towards inside. So it's a, just like a imaginary wall will be creating, and for that reason outside flow will not enter towards inside, or inside flow will not go outside. So this imaginary wall, red line. So this is nothing but basically imaginary wall. I have written somewhere, I think. This is the imaginary wall. And for this we have equation. What is the equation? It's a psi is equal to q by 2. That's all. This is very important. I hope everybody understood. All right.